Hi everyone, welcome to AI Crack channel. This is Akash Kingwar and today we'll be studying AOD lecture 3. So just for the information, QOD series has been paused for now and we'll be restarting it from February. So the first topic we are going to discuss is shortest distance between two non-intersecting differentiable curves. So what do we mean by that? Let's say we have two curves like this. Let's say I take this particular point P over here. Let's call this as curve 1 and curve 2. Now what I'll try to do, I'll try to drop lines from here on this particular curve. So I can clearly see that when I'm reaching a point where this particular line is becoming normal to curve 2, then the distance is becoming shortest, right? But over here, this particular point might not be the one, so that we can find out the shortest distance point between C1 and C2, right? So if I try to move P from here to over here, then what I'll try to do this activity once again. What I'll find, I'm finding that distance is becoming even lesser, and we'll reach a point where we'll find a point basically where this particular line becomes normal to both the curves. So that is the point we have to find out, and that is the distance we have to calculate. So this is the basic idea behind this particular concept. So let's try to see how this happens. So basically what we'll be doing over here, we'll be taking these two curves, C1, C2, and we have to find out the common normal between the curves. So basically we'll be given some kind of data points through which we can calculate the slope of this particular normal, or we can calculate the slope of either of the tangents, basically equal slope tangents. Both should have equal slopes, right? So we'll be having certain kind of data points through which we can either find out the slope of this particular normal or slopes of these two common slope tangents. And that would help us to find out this particular point or this particular point. And that would give us eventually the distance, right? So this is how the process is going to be. Now let us look at this example. Find the shortest distance between the line y equals to x minus 2 and the parabola y equals to x square plus 3x plus 2. Now we have not been given two curves over here. So basically the earlier example which we saw in theory, we saw two curves over here. But over here we have been given directly a line through which we can find out the slope of tangent. So that has been a point through which we can find out the point on this particular curve to find out the distance ultimately. So this situation looks like this one. So we have been given m equals to 1 over here. So basically this particular line has slope equals to 1. So m equals to 1 over here. And if we draw the tangent basically to find out the common normal, we can clearly say that m equals to 1 should be here because these two should be parallel. So we know that y dash equals to 2x plus 3 plus 0, and that should be equals to 1. So that gives me x equals to minus 1, right? We did this because we could find out the slope through this line, and that slope should be equal to the slope of this particular tangent, and we can find out the slope of tangent with the help of derivative. So we got x equals to minus 1. Now we can plug this x equals to minus 1 back in this equation. So we'll be get minus 1 whole square minus 3 plus 2. That would give me 0. So we have got the point as minus 1 comma 0. Now as a property of straight line, we know that if this is a point, let's say h comma k, and if we drop a perpendicular on a line, let's say ax plus by plus c equals to 0. Let's say this is the line. Now if this is the case, then distance d, this distance from this point onto this line, perpendicular onto this line, d would be ah plus bk plus c and divide by under root a square plus b square. This is the distance formula. As of now, you can remember it. We'll be talking about this in the coordinate geometry. So using this particular formula over here, we will find out the distance. So we have got the point, this particular point as minus 1 comma 0, and we have to drop a perpendicular from here onto this line. So we have got the line as y minus x plus 2 equals to 0, and we have got the point as minus 1 comma 0. So basically we'll be getting 0 minus of minus 1 plus 2 divided by under root 1 square plus 1 square, basically 2. So that would be 3 by root 2, right? So this is the distance from this particular point onto this. So basically common normal distance is 3 by root 2. So what kind of variations we can expect in these types of questions? So in this particular question, we have been given slope directly with the help of this straight line equation, right? But that might not be the case in other examples. For example, what can happen? Let me show you one example. Let's say we have been given one example, like let's say this is e raised to power x function and this is ln x. Now we have to find out the distance between these two curves. Either we can do hardcore method of taking derivatives both sides and equating the slopes. That is one way. The smarter way can be, we know that these two functions are actually mirror image of each other are about y equals to x, because both are inverse functions, both are inverse of each other. So now we know that there's one common line in between both of them, y equals to x, that is having m equals to 1. And we can see that the parallel tangents on both of these curves would have the same slope. So we can use these kind of data points to find out the points on the curve and eventually the distance between the two curves. So indirectly or directly, they'll be providing us points or slopes through which we can find out these points and find out the distance. So these are the kind of variations you can get in these types of questions. Now moving on to the next topic, monotonicity. What do we mean by monotonous? So basically, if any behavior is repetitive, so basically if anything is being repetitive, that is called monotonous, right? So let's say if a function is just moving upwards or if a function is moving just downwards, then we can say that the function is monotonic. So basically it's just going upwards, having same kind of property of going upwards, similarly having same kind of property of going downwards, then these kinds of functions are called as monotonic functions. So what are some basic definitions of monotonic functions? So broadly, we have divided into two parts. So let's talk about the increasing part. The vice versa part is for the decreasing. So let's talk about the increasing. So basically upward going functions for now. So we have divided these functions into two categories. So the first one is strictly increasing and the other one is just increasing. So what is the basic difference between these two functions? There's one more caveat over here. I'll talk about it in the later part. But as of now, just remember these definitions, basic definitions. So let's say we have a function over here that goes like this. And over here we have a function that goes like this, right? You can clearly see the difference. So this one is x1, this one is x2, this one is f of x1, and this particular point is f of x2. Similarly over here, this is x1 and this is x2, and let's say this is x3, and this is fx1, this is f of x2, and this is f of x3. Now in case of strictly increasing, definition says if x2 is greater than x1, that implies f of x2 is greater than f of x1. So for all points, if this is the case, then this should be true for strictly increasing function. Now if we talk about increasing function, what we get over here, if x2 is greater than x1, in that case that implies f of x2 greater than equals to f of x1. So this equality is a difference. So we can clearly see these 2 points over here, these two have same value, but there are other points as well. For example x1 and x2, they don't have same values for different x values. So basically as x is increasing, fx2 is greater than equals to fx1, or the point. So these are the two basic definitions of monotonic functions in case of increasing one. So basically strictly increasing and just increasing. Similarly, we have the case for strictly decreasing functions and just decreasing functions. Over here, we'll have the reverse idea. So basically, this sign of inequality would change. So that would become reverse one. Similarly, over here, that would become reverse. So that is the only difference between strictly increasing and strictly decreasing, right? Now, in case of differentiable functions, we have further divided this particular categories into three parts. So this one is exactly the same, but over here we have divided increasing into two parts. Basically, increasing of a different category and non-decreasing. Both are two different categories. So let's talk about these in detail. So strictly decreasing, that means the same. So basically, the function is going just up, and that means the slope is always positive. That means f dash x is always greater than 0. That is very obvious. And since the function is differentiable, we can use the derivative method to find out the conditions. So this was the first case for strictly increasing. Now, if we talk about just increasing, now here the definition is a little different. So basically, this is the case. So what is happening over here? It's f dash x is greater than equals to 0 over here, but that 0 is happening for just one single point. So this slope that is getting 0 over here, that is happening for just one single point and not for an interval. So this is the case for increasing in case of a differentiable function. Now if we talk about non-decreasing function, then this looks like this one. So over here we can get an interval where f dash would be 0. So over here, f dash would be 0 for just one single point, then it's increasing. But if it's non-decreasing, that means f dash equals to f dash x equals to 0 can happen for a particular interval and not for just one single point. So these are the three categories which we have further subdivided, right? Monotonic functions in an interval. So before that, I'll talk about the point as well. Monotonic functions at a point. How do we define monotonic functions? So basically, let's say we have function like this. So this is point called a, and uh, this is a minus h, and this is a plus h. So if we talk about the point, that means f of a is greater than f of a minus h, and f of a plus h is greater than f of a. So this is the basic definition of function being monotonic at a single point. Now, if we talk about an interval, that is a very obvious case that if the function is monotonic in an interval, that means, and let's say this is increasing, the increasing kind of monotonic. In that case, it has to be, satisfying the condition of monotonicity at every single point. So this is x1 and x2. The interval is this one. So this function has to satisfy the conditions of monotonicity at every single point in this particular interval. So that thing we wrote fa should be greater than f of a minus h, and f of a plus h should be greater than f of a. That should be satisfied for every single point. So this is the basic definition of monotonic functions in interval and a point. And what about non-monotonic functions? That is very obvious. So the functions like these ones are non-monotonic. So basically it can increase, it can decrease, it can increase, it can decrease, it can do anything. It can go flatten out and increase and then decrease. Anything can happen for non-monotonic functions. Now, one point I forgot to add earlier. So whenever we are talking about monotonic functions, we define the properties for differentiable functions, but it's not like the functions which are not differentiable, the functions are which are not continuous. We cannot categorize into monotonic or non-monotonic, because the basic definition says if the function is just increasing, be it continuous, be it non-differentiable, be it discontinuous, in every single case, if the basic definition is being satisfied, that function can be tagged as monotonic function, right? For example, we have a function of this sort. So we can clearly see that there's a bump over here, a sharp corner over here, and it's not differentiable at this particular point. But over here, we can see that this value is higher and this value is lower as compared to this one, right? So that means this is an increasing function. This is a monotonic function. Similarly, we can have even a discontinuous function over here. Let's say this is the case. So we can clearly see that this is a discontinuous function over here, and but this value is lesser than this one and this value is lesser than this one. So basically it's a continuous function, it's a monotonic function, not continuous, right? So you got the idea about it. So let me clarify the confusion between increasing and non-decreasing function once again. So because in the basic definition, we saw that we have categorized into just two parts, strictly increasing and increasing. And in case of increasing, we saw that we can either have this one or we can have just this one, right? Where the derivative is getting zero at just one single point. In case of basic definition for all sorts of functions, this particular definition is this particular definition combines two types of subcategories. So that's why we divided this in this category into two parts. That would be increasing and non-decreasing. In case of increasing, we'll be having just a single point where this function, where the derivative becomes zero. In case of non-decreasing, it can become an interval where this entire range this particular entire range is having f dash equals to 0. So we have just divided into these two parts. So basically, whenever we are being asked in the questions, if the function is strictly increasing, f dash greater than 0. If the function is increasing, f dash greater than equals to 0, and at a point 0 thing, that 0 point should come at just one single point, and f dash x greater than equals to 0 for an interval, then it's non-decreasing. So this is how we have to define the functions. And over here it's not one single point, basically discrete points. It can be like this one or this one. So we're having two discrete points where function f dash x is becoming 0. It's not, but it's not an interval. So the main point is it should not be an interval. Now let's look at this example, fx equals to x square minus ln x. So we have to find out the range or interval of x where this function is strictly increasing or strictly decreasing. Right? Let's talk about strictly increasing. So basically f dash x would be greater than 0. So 2x minus 1 by x should be greater than 0. Now if we talk about the domain over here, x should be greater than 0 because we have ln x over here. So this gives me 2x square minus 1 divided by x greater than 0 for strictly increasing. So this gives me root 2x plus 1 root 2x minus 1 divided by x greater than 0. Now using the wavy curve method, for denominator we'll be getting x equals to 0. For this particular point we'll be getting 1 by root 2. For the other point we'll be getting minus 1 by root 2. Plus minus, right? Now we can clearly see that we are getting 2 plus points over here, but the main thing is this is not in the domain. We just want to find out the points where x is greater than 0. So only this particular range is in domain. So our answer should be for 1 by root 2 open to infinity. So this should be our answer for strictly increasing, and for strictly decreasing our answer should be this one. So basically 0 to 1 by root 2 open bracket, right? So this is how you have to find the intervals of strictly increasing and strictly decreasing. If they would have asked us for strictly increase and just increasing or just decreasing, then the answer would have been different. Now let's see this example. Separate the intervals of monotonicity for the function fx equals to 3x4 minus 8x cube minus 6x square plus 24x plus 7. So basically we'll be finding out f dash x equals to, that would give me 12x cube minus 24x square minus 12x plus 24, right? So we'll be taking out 12 as common. That would give me x cube minus 2x square minus x plus 2. Now I can clearly see that 1 is a root of this particular equation. So 12x minus 1. And now we'll be factorizing this remaining equation. So we'll be writing x square because we need x cube over here, but this is giving me minus x square as well. But we need minus 2x square. So what I'll be doing, I'll be writing minus x so that I can get the additional minus x square. Now this gives me plus x from this, but we need minus x. So I'll be writing minus 2. That gives me minus 2x and also plus 2 over here. Now this again becomes very simple. 12x minus 1, x plus 2, and x not x plus 2, x minus 2, and x plus 1. So this is our final factorized equation for f dash x. So basically we have to find out the intervals of monotonicity. So basically we'll be using wavy curve equation once again. So this is x equals to 1, this is x equals to 2, and this is x equals to minus 1. So plus minus plus minus. So for strictly increasing, we'll be getting these points. For strictly decreasing, we'll be getting these points. So this is how you can do it, right? So these are the kind of standard examples you can expect in PGDBA examinations. They won't be asking you a very difficult JEE Mains or JEE Advanced types of questions in case of this particular topic of increasing or decreasing functions, right? So today's lecture was still here only, and in the next lecture we'll be seeing local and global minima maxima concepts and few other theorems like LMVT and Rolle's theorem. So let's meet tomorrow, and thanks for watching.